This is the CapEx IndustryCast, and last week we had Gordon Spleet on, and he has graciously allowed us to use his time again to talk about troubleshooting leak test equipment. So our mission here at CapEx is to offer as much value for our customers every day, so we can be adding value to you. Ideally enhancing your career, making your work easier because you're using the technologies that we are applying. So again, my name is Russ Sorrells, and I am one of the account managers for CapEx. I've been doing this or working with leak test equipment since 1994. So Gordon Spleet and I have been working together that many years this week, because he and I started working together back in 1995. So Gordon is a senior person there at Cincinnati Test Systems. Gosh, I mean, you have to be one of the longest tenured, huh, Gordon?
Oh, we've got a few older than that. Jeff McBee, 30 years.
Wow.
A couple of our engineering specialists, 32 and 35. So yeah, it's we've got some experience at CTS.
That's awesome. How many years has Doug Teeter been there?
He's been there just slightly less than me, probably around 23.
Yeah, no, he's a fellow Boilermaker. So, again, our mission here is to add value. Thank you so much, Gordon, for joining. Let's just hop right into this. Let's talk about troubleshooting leak test equipment.
Oh yeah, so the biggest thing, seals. If you can't seal a part, you'll never be able to leak test it. And we find those are the biggest causes of problems for leak testing. Seals that are not compressing evenly on a large surface area. So you can see in this picture, there's a large flat cut seal. And if that doesn't come into a part as flat as possible to the surface it's going to contact, and it's got a slight angle to it, you could end up burping through that seal during test. It may not bubble all the time. It may just come to a certain pressure and then eventually emit some air pressure from the part. And it's not a constant leak, but it's a form of weakness because of your alignment of your seal. The other thing that will cause that is seal wear. So if you're not compressing it well enough, coming to a positive stop, and it's wearing and your seal is floating from the pressure emitted from the compressed part or from the pressurized part, then you're going to see some seal movement from that standpoint too.
Yeah, that makes a lot of sense. What are the so cutting the seals? Is that a result of too much pressure and not having hard stops? Like, what are some of the common causes for those issues with seals?
Yeah, exactly. So two things can cause excessive seal wear. Oh, two specific things: sharp edges. If you're sealing against a sharp chamfer, that will eventually cause the seal to cut. If you're coming into a flat surface that is actually narrower than your seal area, then you'll end up cutting into the seal with that sharper surface. The durometer of your seal material, if it's not a hard enough durometer, it may cause wear very easily and cause those leaking issues as well.
A common one that I recall from back in my days, at one point in time I focused on, or I covered Wisconsin, right? And in Wisconsin, there were a lot of die cast companies that would die cast and then machine their parts. And the machine parts, a lot of times would have coolant on them, or sometimes the soaps that they were using would have a residual. And I remember them getting sticky, and it would actually pull the seal out of the part. And they'd ship that part, and then they go to test the next one, of course, and it wouldn't seal because the seal was on the part that they just shipped because it stuck to it.
Yeah, we see that a lot too.
On that?
So
other than washing parts better.
Yeah, so the key to that is actually designing your retention device so that it's got more of a dovetail rather than a flat area that you're compressing that seal into. So
yes. Okay, so when you insert the seal, it is locking in so that it is not as apt to stay with the part.
Yeah, exactly. Yeah, and sometimes if you dovetail that a lot, you need to put uh, some relief to atmosphere. So that way, if your seal is causing some wear and you're pressurizing your part, and you run the risk of then pressurizing that dovetail area within the seal area itself. So making sure that you don't have virtual leaks in the way you've designed your seal retention devices is also important.
Yeah, that makes a lot of sense. Otherwise, you're going to have virtual leaks, right?
Yep. Yeah, exactly.
Common problem. Okay, so causes of variation. We're talking about fixture sealing design. So
Yep.
talk through this.
Yeah, so cylinder size, making sure that the amount of force to seal your part is at least 1.5 times to 2 times the opposing force on that surface area after you've pressurized the part with test pressure. So having large enough cylinders with enough pilot pressure to hold those in place.
Looking at this sealing surface that you've got here with this picture, that is a huge area. Can you imagine if you just pressurize it to 50 psi, the amount of force required to keep that down?
Oh, absolutely. It's immense. Um, the key to that is designing your seal so that you can compress it and then bring it to a positive stop. That's why you see those two pictures in the middle, the cartoon pictures in the middle here, is designing your device so that when you compress a seal, it brings it to a metal to metal stop somewhere with either your fixture design or the machine face to the machine face of your tooling plate.
Yeah, that's a great point. One thing that it would be a good reminder for customers to wrap their mind around is remember that with every leak test, we are measuring essentially pressure change, and so anything that affects the pressure change of the part, and this is mass flow or pressure decay, is going to affect the results, the repeatability of that, and our ability to accurately determine is the part leaking or is it not leaking? So as you can imagine, when we're thinking about the surface area that we're considering here, if just 1,000, 2,000ths of inflection of that part is going to change the volume inside the area that we're testing. And of course, what happens when you change the volume? You change the
Leak rate.
well, you change the pressure, right?
Yeah.
So
Oh,
yeah,
yeah.
but that's going to change, and that's going to affect the leak rate.
Right.
Yeah, absolutely. So
Yep.
yeah, so I always, just try to get customers to wrap their mind around the fact that we are measuring pressure change, pressure change, pressure change, and anything that affects the pressure inside the part, whether it be heat, whether it be excess, fluctuation of air pressure in the facility, barometric pressure changes. I mean, we've
Mm-hmm.
seen it all, right? So
Right. Well, and another way to visualize this is a volume. If you have 1 millimeter of movement across that 20 square inches of surface, that equates to a volumetric change, and that's measured, like you said, with a pressure change correlated to a volumetric flow rate.
yeah, and the sensitivity of the instrumentation is just tremendous. It picks it up because that's what
Yes.
we want it to do. We need it to in order to determine these very small, differentiate between these very small leak rates.
Right. And then getting to your point of seal wear. So if you've designed your seals with positive stops and you've got a lot of force to push it down to come to a positive stop.
Mm-hmm.
However, if you haven't designed your seal for the right amount of height and compression, you will eventually squish that seal to the point where you cut it in a very quick amount of time. And that's
Yeah.
another area of wear. So designing it correctly is hugely important.
Yeah, the goal is to compress it, not extrude it, right?
Yes, yeah.
Yeah. So, all right, excellent.
And then
Um,
seal durometer, like we were saying earlier, having the right durometer so that you're allowing it to compress and not compress too much where it causes excessive wear. And if you have high pressures, It doesn't just have to be a 70 durometer. It can actually be a 70 durometer with fiber fill. That way you actually give it some tensile strength so it's not cutting easily.
Yeah, and that's something else that that over the years, Cincinnati Test Systems has really perfected, and is that that material where before it was just straight up polyurethane, but we've done a lot of development in making sure that it is, like you said, fiber reinforced to help its durability and longevity.
Right. And now we can talk a little bit about cylinder pressure too. So you can see the test system in the bottom right-hand picture. That's got some really large cylinder valves
Yeah.
or cylinders. And those are all air actuated. The key to those is not just the fact that they're air actuated. If there's any fluctuations in air, those cylinders could back off. So what we also add to those are rod locks. So
Mm.
once they're in place, they actually get locked in place by a little lower pressure so that it can't move under test pressure.
Yeah,
And
that brings me at one point. I remember many years ago, many years ago, when I was still in Wisconsin, we were working on a machine for one of our big motorcycle customers,
yeah.
and it was a dual station machine, and we'd run one station, it would be great, and then we'd go to run the other station, and every now and then there was a gremlin, something that would show up that threw our numbers off. We just searched and searched and searched and searched, and we'll come to find out what was happening was when we would activate station one, doing some troubleshooting and working on it while we were doing our testing on number two. Station number one was affecting station number two's ability to get a repeatable test. So we separated the air sources from each station, and that resulted in eliminating that problem. But so that's again a cylinder. So what would happen was, as we would activate station one, it would, it takes a lot of air to move those cylinders,
Mm-hmm.
and that would lessen the available air that was holding the cylinders and pressing and sealing off on the part. That would just relax them just slightly, and of course that would in turn change the volume, which would in turn change the leak rate
Yeah.
when the test was complete. So
Yeah. Air accumulators, regulated air accumulators at your test cell helps to reduce that type of fluctuation and problems.
absolutely, yeah, especially on those high pressure applications. Cool. I got all excited to talk about that example. Anything else to hit on here?
Oh, just the fact that depending on where your air movement is or the movement of your part seal, you're either going to have false accepts or false rejects. And that it depends on which direction it's moving while you're conducting your testing.
Yeah, right on. Oh, something I'd be careful of as well. One, this is mainly with helium testing, I guess,
Mm.
is when that tracer gas gets stuck in those O-ring grooves. That's for
Oh,
another day.
yeah.
That's for another day of discussion. We're talking about mass flow, pressure decay, differential leak test troubleshooting right now. So, okay, next
Yep.
one.
Oh, yeah. So fittings. Everyone loves push lock fittings. They're
Yes,
so easy to
very
use and
easy. Yeah.
great for maintenance. Remove uh, your hose, throw it away, start with a new one. The biggest problem we find with push lock fittings is their repeatability over time. So they will cause, it's an O-ring that has a tube that fits into it, and eventually that tube will either wear or have uh, scribe marks from debris and causing leaks. And the O-ring compression may have some issues. Our suggestion: never use push lock fittings on your test lines. Use them on your pressure coming to your test instrument, but on the test line side, use a compression ferrule style fitting. That will give you a positive lock on your tubing, and um, using the right types of fittings, MPT fittings with either Teflon tape or SWAC. We've really migrated a lot to Teflon tape rather than using SWAC because of the uh, the gooiness of the use of slack. Um,
Really?
yeah,
So I remember, and my apologies for taking us back in time, but some of the challenges that I had with piping that customers would do was because they would get the Teflon on the tip of
mm,
the tip of it, and it would actually end up in one of my valves. And
yeah, yeah. So that's the caution of using Teflon tape is when you wrap it, make sure it's not wrapped over the end, and it's just you allow some thread grip and then into the tape. So that's some of the keys to using it.
absolutely, now
Mm.
test line tubing.
Yeah, and then test line tubing. You heard me say a positive lock on your tubing. Well, if you have thin wall PVC tubing, you're not going to get a great positive lock. And then two, thin wall PVC or even rubber is going to expand under pressure. So you're going to see that same movement we were talking about earlier where volumetric change is equated to an actual leak rate and false accepts or rejects based on its expansion contraction. So our suggestion, 500 psi nylon style tubing or higher. We use a lot of 1,000 psi rated tubing,
Yeah.
and
And
it
it's like testing a balloon, right, over time, and especially with pressure decay, differential pressure decay. Those are volume dependent technologies that we're using. So so you calibrate with one volume, and then over the course of time, it changes. You're not even performing the same test because the volume now differs.
yeah, absolutely. And using rated tubing that at least is higher than your test pressure too. So definitely, if you're using pressured lines coming to your station and your 100 psi source, I wouldn't use 100 psi rated tubing. I'd use something higher than that.
Yeah, absolutely.
All right, so here's the part of troubleshooting that we like to help our customers with with machinery is some training. And with training, it includes maintenance training and then what are spare parts. So
Yeah,
at runoff, we'll supply operator training during a runoff sequence. And I've got a picture here of a test system. This is a simple simple C20 uh, instrument integrated with two sets of tooling. And if the operators don't know how to use this, they may always test tooling in station one and not get it correlated correctly when they change over to station number two.
mm,
And then there's a lot of manual locks on this. See all the Destaco clamps and
yeah,
integrated with CTS Connects. And there may be a correct operation for bring this into place first, this clamp, and then the seals come into place versus bringing a seal in before the part's clamped. You can cause excessive wear the way that you seal parts if it's not clamped in place correctly. So those are all the things to help understand how the machine's supposed to operate to help keep it maintenance free or problem free.
and of course this should all be part of the standard work for these stations. One would hope, right?
Mm-hmm. Absolutely. And the keys to the maintenance department for correct operation. When you start working with an instrument, suggestion, always back the system up. Or
Hmm.
that way, if you make some changes that weren't correct, you can always go back to the way it started.
Yeah, especially nowadays with just popping a memory stick in there and doing a quick backup, it's no time and a no brainer, right?
Yep, absolutely. All our instruments have a USB interface for backup and restore.
Man, if only the I-21s had that.
Well, that's why we help our customers replace those as they wear them out. Those were a workhorse. We still see them in operation even from 25 years ago.
Yeah. So yeah, for those of you that don't know what an I-21 is, it is an instrument that we've had around since, gosh, when did that come out? That was probably about 90,
95. Yeah,
95.
I was hired to help support those efforts. So
Wow. Awesome.
yeah,
All right, next.
so understanding what your spare parts and where items are, that's always important too. Where are the O-rings? Where are the seals? What are the valves that you may have problems with? We suggest for parts that may have debris in them. You were talking about debris earlier and possible cutting fluids. So putting an external exhaust valve close to the part. That way you're not exhausting all that debris up through your test line and through the instrument during an exhaust cycle.
Yeah, that's something to keep in mind and mention. And I know, most customers probably know this, but with the instruments, the only way that we can exhaust air in a standard instrument is back through the manifold and out the exhaust valve in the muffler that we have on the side. So the way that, or down below. So what Gordon is talking about is actually mounting a valve externally so that the air, when it's released, doesn't go back through the instrument. It exits a valve that is external to the instrument to avoid getting debris into. Now, of course, the debris can get in the exhaust valve, but that's okay. That's the reason it exists. So we just have to troubleshoot that aspect.
Yeah. Yeah, exactly. Knowing where the maintenance items are on a test stand is really important for helping troubleshoot it, and having drawings and manuals.
How many times have we chased our tail? My goodness. I remember one time I went to a customer, this is when I was in Michigan, and they had a C20 and they had made their own fixturing and everything else. And they called me in, of course I got the call, Russ, your piece of crap instrument isn't working, get in here. So I got in there that day, that afternoon, and right around lunchtime. And I spent the entire, it was just blowing my mind. I couldn't, the instrument was fine. I did the self-test, all of that, just searched and searched. I mean, soapy water, every fitting, everything. I mean, it was just, there was nothing leaking. And finally I had sprayed so much soapy water that it began to run over the side of the fixture and off the tooling plate and onto the actual table. And I hit the start button one time and I saw air coming from between the tooling plate and the table that it was actually sitting on. And I said to the customer, I said, unbolt this thing. Let's look underneath this. Sure enough, they had gun drilled it. They drilled it tried to drill it about 12 inches into this plate, and they had drill run.
Oh,
And so it had exposed underneath. They had a hole in the bottom of their fixture essentially, and until the bubbles came bubbling out, it was one of those you never can find. It's just sometimes it's tough. So
yeah,
sorry to get
absolutely.
sidetracked on that. I just remember that because I was there for 6 hours as we tried to figure this out.
Yeah, and like we just said, using your drawings to understand where the trouble spots could be. Absolutely.
Yeah, and it's just chasing it back. So often it's chasing it back, and one of this was a CTS service person that taught me this is if you have a dual station machine, taking the instrument. So if you have a problem on one station and you're not sure if it's the instrument or the station, just taking the airlines and switching them, swapping them to the other to see if the problem stays with the instrument or stays with the fixturing. That has saved me multiple times on dual station machines for sure.
Absolutely. And if you look at the system troubleshooting training, simple checks, the very last bullet, that's exactly what you just said. On a multi-station system, switch test lines and compare results.
Yeah.
That will help you every time. The other thing is use the instrument self-test caps. Start with the instrument, check to make sure it's not in the instrument, and then work your way out. Test lines, cap a test line before it goes into tooling. Make sure it's no fittings or valves in the test line. And then go to your tooling and then work through every one of the seals like we talked about earlier. Uh, are they burping? Are they actually leaking all the time? Are they wearing?
Absolutely. The first thing, so when a customer first gets an instrument, or if I'm working with a customer to train them, I said the very first thing that you do when you're operator says this instrument's messed up or there's a problem, is just put that self-test cap in and perform a self-test.
Yeah.
And then if the self-test comes back good, now you can begin the troubleshooting process. And it just eliminates so much headache if it is the instrument, if debris got in the manifold. And that's the most common problem that we see, of course, is debris gets into the manifold and it's actually not allowing the valves to seal properly. So we have what we call an internal leak inside the instrument, and the valve needs to be, essentially rebuilt or the manifold swapped out. So that's the most common problem as it relates to the instrumentation. But the another very common issue, I don't know if it's addressed in some of this documentation, but is that the setting. So the operators, or the customers, when they go to set them up, let's say their target pressure is 20 psi. They set their target, their upper limit to 20.1 psi, and they set their lower limit to 19.9 psi. And what happens is, the instrument, of course, is trying to hit that window that we've set, which is essentially 0.1 up and 0.1 down. It makes it very difficult. So when you go to run the test, if it's not in that window, the instrument gives you an error. So there's a test pressure low or a test pressure high error. And oftentimes customers that confuses them because they're like, oh man, it's hitting the pressure, but as soon as it goes into the stabilization, the pressure starts to go down a little bit and it drops below the minimum pressure. And of course that triggers a fault in the instrument. So it's important that we have an appropriate plus minus window on our pressure. I always, target 10% with customers, 10% up or down. And just as a starting point, is that something you've seen pretty common?
Yeah, absolutely.
First
And yep, calibration verification, and also setting your windows to meet those really tight's not the right term, but making sure that when you calibrate the system, you're not calibrating two problems.
Yes, yeah, for sure. And that is
And that is a window I forgot to add into this slide for you, Russ, was the performance factor. What that means in coordination with your high limit measurements and your master leak loss, master no leak loss.
Yeah. Oh, that's a great point. So let's just kind of step into that. I'll mention that to customers. So one of the unique aspects of our Cincinnati Test Systems instruments is that when we do a calibration or perform a calibration, it comes back as a performance factor. What are we calling it nowadays, Gordon? It's performance
yes, it's performance factor, and
yes.
it
We used
started.
to call it calibration ratio.
Yep, it started that way, and the cal ratio, master no leak plus leak. That's your rejected part measurement during calibration minus your no leak loss factor. That's your zero leak pressure loss. That whole quantity divided by your no leak loss, by your master leak loss factor, which is your known good part measurement with a leak standard in it. So that ratio allows you to understand the difference between your good parts measured and your bad parts in the calibration process.
The best we can get is 100,
Yep.
right? And so, and just depending on the part size and some of the complexity and a number of different factors, we may say a performance factor above 40 is going to be acceptable for the application, or maybe we can achieve a performance factor above 60, and that's going to be acceptable. But it's it seems in my experience, it's been very application dependent as it relates to what performance factor number is going to be acceptable for your application.
Yeah, the test pressure will affect it, your leak rate will affect it, and the size or the volume of your test air space, the volume of the part will affect that.
Yeah, and so oftentimes it's just a matter of learning what that number is for your application, but a really good tool for referencing, is this a good calibration? So when you get a good calibration or achieve a good calibration, now that becomes your point of reference. So if it's 56, then anything less than a 56 performance ratio could be suspect as it relates to calibrating problems into the calibration process.
And then the next slide talks about how you validate that calibration process. So now you've calibrated your system, and that's something to understand. Every time you make a change to your system, you want to recalibrate it. And to validate or verify you've got a good calibration, check your performance factor first, and then you can have a mastered part with a leak standard built into it, 10% above and 10% below your reject rate. So that's two additional master parts, one above, one below your reject rate. Test those and make sure you accept one that is below and reject the one above, and that you're measuring within that percentage of window for that expected leak rate or measurement of those parts. And if you're
Oh my
not,
gosh, Gordon, I mean, that's so much to do. And gosh,
it's easy.
all these things, right? But that, from a verification perspective, that's what you want, right? You want to make sure that the tool that you're using, the gauge that you're using to measure is accurate, right?
Yep. Accurate and accepting and rejecting the parts you need to find. That
But
way.
let me ask you this question, Gordon. This is the most common question that I get is, how often should I calibrate?
It does depend on your application, your manufacturing process. We have some customers, they calibrate at the beginning of every shift. That gives you the most capability for adjusting to ambient temperature changes that may occur through your plant, whether it's a morning shift, an afternoon shift. Maybe you, maybe first shift you calibrate the beginning of the day and after lunch to accommodate the ambient temperature change in your plant. Some customers have really large leak rates. They may just calibrate once a week or once a month. It all depends on your process and how much it could change um, based on other variables and conditions of your manufacturing environment.
One of the things I always tell customers is you have to remember that every time that you calibrate is an opportunity to screw something up. Now,
Yeah.
not to discourage them from calibrating, but to keep in mind to not do it just willy-nilly, to
Right.
have a reason to recalibrate and make sure that they're using, good parts and everything is sealing properly, their seals are clean, everything that goes into ensuring that we've got a good calibration. You want to make sure that you're repeating that process every single time.
Yeah. Yeah. And that's one of those where if you do calibrate a lot, I would validate that calibration process or do just a verification test. And if it accepts and rejects within those measurements, you don't have to recalibrate. Your system's already set up.
Yeah, what a lot of our customers do, just so as, I know it seems complex here. If you look at the bottom, it says utilize no leaking part, then part A, part B. What you can have is one part, and you can cap off a quick connect on that part. That can be your no leak, and then you can put in the leak standard for the upper limit, verify that it rejects, and then you can put the leak standard in for the lower limit, make sure that that accepts. So you can use the same part, just have a quick connect that allows you to clip these leak standards in and out.
Yep, absolutely. Well, you know what? We're going to do this a couple different times. The next time that we get together, Russ, we can plug our MH instrument into a shared screen and real life change those through a screen that makes it real easy and takes
Oh,
some
that would be
people through it.
cool. Yeah,
Yeah.
that would be so cool. Because in looking through or in talking through what we're talking now, this is great information. I've got another slideshow that is specific to conditions and talks about, kind of stepping through that troubleshooting process as well. So yeah, we'll definitely do this again.
All right.
All right. We are, grateful for the opportunity to serve our customers. Again, our mission is to always be adding value at CapEx. That goes with Cincinnati Test Systems as well. Gordon has a wealth of knowledge. His information is right here, and he is happy to share that with you. If you are in North Carolina, South Carolina, Virginia, we welcome the opportunity to help you out with your leak test equipment. I have been, Gordon and I have been involved in leak tests for the last X number of years of our career. So we've learned a lot along the way, and we love sharing that information. So, Gordon, thank you for your time as always. Anything to add here as we wrap up?
Well, there's so much to say, Russ. We just appreciate everyone's partnering with Cincinnati Test Systems and look forward to supporting all the leak testing needs of every industry.
Absolutely. And as always, thank you, Gordon. Appreciate you. Anything comes up, let me know. Again, my name is Russ Sorrells with CapEx Sales. Have an amazing day.